Okay, so last time we did the basic maximum margin classifier, and the upshot of it was that we wrote some code that found this maximum margin for some toy data, and there was the code. And that was to kind of help you understand how the project basically works. Um, so now what you have to do is fill in similar code, but for the soft margin classifier. So let's talk about what the soft margin classifier is. Let's go over to the notebook for a second. So, most data is not linearly separable. So let's say that this is some kind of separator function that occurs in nature, and now we look at some data, and almost all the data is like that. And there's some other data that's like this over here. But there's one weird red one over there. Um, and let me just emphasize that, so we can get a better sense of the distribution. So probably making the decision boundary where it is right there is best, but the maximum margin classifier will not like that because it has an error, right? Because it it will not tolerate this misclassified point. It'll find the one that minimizes the error function or the objective function while satisfying all of its constraints. So in order to satisfy all of its constraints, it has to make this ugly green line that I just drew. And that's going to perform worse in the future because you're probably going to get some red ones over here and you're probably going to get some green ones over here. So that boundary is really not the best. Plus you have the possibility that the data is not really linearly separable at all. So the solution that I think it's Vladimir Vapnik came up with when he invented the support vector machine is to introduce the concept of slack. So what we're going to do is we're going to have a margin, and we are going to still talk about the maximum margin classifier, which I'm drawing the maximum margin line here. But we're going to build into every data point a little bit of slack. So let me see if I can get a good slack color going here. So every data point has a budget of slack. So this data point here is going to have, we denote the slack with a variable zeta, which I haven't made in a few years. So zeta relates to the length of that line right there. And this would be kind of a big zeta. And everything that's correctly classified doesn't have a zeta at all. So everything that's on the wrong side of the margin gets allocated a little bit of slack. Every variable has an associated slack variable. So if this is data point, like, let's say that happens to be data point x22, then this is the corresponding slack variable, zeta 22. And that value, just to give it a name, would be something, let's say it's like 2.6 or something like that, okay? Now, all of these points that are on the right side of their margin, let's say that this variable is x10. This variable also has an associated zeta variable, but because it's on the right side of its margin, its zeta value is 0. And all of these zetas, zeta I for every I, is always greater than or equal to 0. So for points that are on the correct side of the margin, the associated zeta value is 0. And if you're sort of in this zone, like right here, if let's say we put a red point like right there. So if a red point was right there, then the associated zeta value would be something between, so it would be some kind of zeta that would be like roughly 0.5. The important thing is that it would be between 0 and 1. And then once you're actually misclassified, so this line, if your point is on the decision boundary, if there's a red point on the decision boundary, the corresponding slack variable zeta will just be 1. And then as you go further and further over here, the slack gets higher and higher. Okay, so that's slack variables. Now let's go back to this sheet and we can read along, and maybe this says the same thing. We can kind of try to understand it better. Okay, so for every training point, we associate a slack variable. The slack variable measures how far the data point is from being on the right side of the margin. If the data point is actually on the correct side of the margin, then zeta is 0. And so in the hard margin optimization problem that we discussed in the previous video, this was the constraint. But now for each data point, we actually have two constraints. One of them is that this quantity on the left here is greater than or equal to 1 minus the slack for the variable. And we also require that the slack variable is always positive. So this is twice as many constraints as we had before, because now we have a constraint for each slack variable, and also the form of this constraint is a little bit different. Let's just think about this for a second. So suppose that W is such that this variable x is on the correct side of the margin. Then this is going to be something greater than 1, and the slack variable is going to be 0, because we haven't gotten to the objective function yet. This diagram, I apologize, these variables are not zetas, they are kz's, but I found this on the internet. It's not a bad picture. It shows you that these associated slack variables are all 0 when you're on the right side of the margin. If you're in here, then your slack variable is something between 0 and 1. And then for the really bad ones that are all the way on the other side of the decision boundary, their slack variable is greater than 1. So now let's write down the actual objective function and the actual constraints. So this was sort of what we wanted to minimize before. And now we've got this new term. So this 1/2 WTW, this is exactly what we were minimizing before. It's just the sum of squares of the non-bias weights. And now we've got this extra thing, and so this is kind of like the slack penalty. So it's the sum of all the slack variables, and then there's this this constant c, which is an adjustable hyperparameter. It's a value that you choose that sets how much you care about correct classification versus like a better generalization. So that is kind of a confusing statement. So let me see if I can explain that trade-off better. So let's draw a decision boundary, and let's draw some data. Actually, let's start with the data. So let's say I have some green ones up here. So you can get a sense for what that distribution looks like. And I have some red ones down here. Okay, and now there's one outlier red one right there. Okay, so let's think about what kind of decision boundary. I think I'm going to copy this so that I can paste it again later. This might be useful because I'm about to mess it up. Okay, so now let's draw. Let's say we have to decide on a decision boundary. Let's say we choose this decision boundary. Okay, so this decision boundary has good generalization because this red one is obviously an outlier. So this one is probably going to perform better out of sample. And okay, but it tolerates a misclassification. So what is the total slack budget for this one? So the slack budget, or I guess the slack budget that's being used, is we have to pay quite a bit of slack for this one thing right there. So let's say that this happens to be, x12 or something. So zeta 12, I almost drew a kz. I kind of like kz better, but I said I would use zeta, so I have to. Okay, so zeta is going to be something like, let's say that it's like 2.6. Okay, now we're using a slack budget of 2.6. All right, and so what is the right? And we've got the margins. The margins are pretty wide here. So the margins are wide, and because the margins are wide, we have this quantity 1/2 W1 squared plus W2 squared. Let's just say that there are two weights there. This is going to be pretty small. How do I know? That's because the margins are wide, and wide margins means that this quantity is small. Okay, now let's adjust this a little bit and look at a different scenario. Now we'll see if I can paste this thing that I saved. Yeah, it looks like I can make it a little bigger perhaps. Okay, so all right. Now let's look at an alternative way to deal with this situation where we really don't like slack. Okay, so here's a decision boundary that gets perfect classification, right? Perfect classification. It makes no classification errors, but it has a very narrow margin. It has a very narrow margin. You can see that this little corridor here has to be kind of skinny. So now what is this? This means that the associated hyperplane that's making this decision boundary is very steep, which means that 1/2 W1 squared plus W2 squared is pretty big because those margins are so tight. And now let's look at what's happening with the slack. Now the slack budget is 0 because every single point is on the correct side of the margin, so I'm not using any slack whatsoever. So what this quantity C lets me do is trade off against these two scenarios. So let's suppose that in an extreme case that that C is equal to 0. So that's an interesting extreme case, right? And so what is C? You might have forgotten by now. C is this hyperparameter right here that controls how much we care about slack. So if C is equal to 0, that means that all we care about is having very wide margins. And so what are the constraints going to be then? Yeah, so we don't penalize having huge slack. So actually it's kind of unpredictable what's going to happen here because it doesn't care about slack at all. So it's just going to try to have the biggest possible margins. Yeah. Subject to what kind of constraints now? So now we're going to be looking at constraints that look like this. WTXN, so this is going to be greater than or equal to 1 minus this. Okay, and now we don't care how big zeta is anymore. We just have to satisfy this constraint. And okay, so we can't tolerate, I don't know. I guess I'm confusing myself here. So let's say that we care, instead of saying 0, 0 is kind of blowing my mind a little bit, okay? So instead of making C 0, let's make it a small number like 1/10. Okay, all right. Now that means when in our objective function, when we're minimizing this quantity, the most important thing is going to be the widths of the margins. We're mostly going to care about that. We're not going to care very much about the slack. So, you know, this is only going to contribute like 0.26 to the value of the objective function when C is equal to 1/10. And when C is equal to 1/10, let's come and look at this other picture too. All right, so if C is equal to 1/10, the slack budget is actually 0. All right. So which kind of decision boundary would you get if C were equal to 1/10? You might get something kind of like this, okay? Where you tolerate a little bit of slack because this slack isn't being penalized very much, and what you get is you get this being small. So this would probably be the kind of decision boundary you would get if C was like a small positive number like 1/10. Now, as another thought experiment, let's make C equal to an enormous number. Let's make C equal to 1,000. So if C were equal to 1,000, well, we're going to change our assumption here. C is equal to 1,000, then instead of this little bit of slack contributing 0.26, now it's going to contribute 2,600 units. And so that's going to probably going to outweigh the width of the margin. And what it's really going to care about if C is equal to 1,000 is making sure that the slack budget is as small as possible, because slack here is being heavily penalized. So if you make C go up to 1,000, then the kind of decision boundary it's going to find is one like this, where the slack budget is 0. So as you change the value of this hyperparameter, you change the emphasis between perfectly exact classification. That's when C is large, you value perfectly correct classification. And then as you make C closer and closer to 0, you favor more and more the generalization. You relax the boundary, and you just try to kind of get things correct in like broad strokes. So which value of C is correct is gonna be a function of the actual data set that you have, and you have to experiment and see which one works using a technique called model selection with a validation set, which is a topic for another day. But that's what C is doing there. Okay, so this is the objective function. C is a hyperparameter that we choose. And now everything is subject to these constraints. So the constraints are that this product is greater than or equal to 1 minus the associated slack variable, and the slack variables are all positive. Okay, so now some things have changed. Now we're going to code this up again, just like we did last time. And so let's go over here and let's reintroduce our green red convention here. So when I write W in green, by that I mean W1, W2, W3. And in this case, we're going to have an explicit bias, which is W0. But if we write things in red, what we mean is the bias is just built in here. So it's W0, W1, W2, W3. So in these notes over here, this would be the green W because it's not including the bias, and this would kind of be the red W because it is including the bias there. So let's write down what we want, and let's so we want W. Oh, we want green W, right? We want green W transpose times green W. I think before we wrote this as W squared, but these are actually the same quantities. No matter which one you use, it's still just the sum of Wi squared. So all three of these are saying the same thing. So pick your favorite one. I'm just going to say the top one because that's what it is saying in the notes right now. Okay, and then there's this factor of 1/2 that's just there for algebraic convenience. And we also want to minimize C times the sum of the slack variables, which are all positive. Okay, and I is going from 1 here to n because that's how many data sets there are. Data points there are. And okay, so let's compare this now to our general quadratic function of some variables. So we have to somehow translate what I just wrote there into a quadratic programming problem. And remember, a quadratic programming problem looks like this in general. So it's A transpose times Z. So here I'm deliberately not using W, I'm using Z here. And so here I'll do the quadratic programming for you, but if you don't want me to, you might want to pause the video and think about it yourself. That'd probably be better for you. So what is Z going to be? So Z is going to be, the first part of it, we'll just let it be all of the W's there. Actually, we want it to, do we care about? I'm going to throw in the bias, okay? W1, W2, dot, 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 up to WD. Now, this is just the dimensionality of the data. Sometimes we call that M, sometimes we call it D. I'm sorry for the changing things around a bit there. And now I'm going to list all of the slack variables. So here's the first slack variable. Here's the second slack variable. And there are as many slack variables as there are data points. And so I'm going to use lowercase n to represent the number of data points. Okay. Now let's think about what G and A could be to make this work. So we want this to be true, right? G times Z is equal to 1/2 blah, blah, blah. Let me go back and look at the quadratic programming problem here. I'm not 100% sure. Okay, so this 1/2 is there. The 1/2 is, it's just I'm going to put the 1/2 here just to make them match up, all right? So we'll say that 1/2 is there. Okay, now the big question is, what is G going to be? So I'm going to write G in block matrix form. So I don't know if you've ever seen block matrix form. So let's look at sort of like, let's make a little corner of G up here, which is D plus 1 by D plus 1. We'll have a little submatrix here, and it's going to be basically the matrix that we had before, where it's like the identity matrix. It's all zeros over here. It's like the identity matrix, except for the upper left one is 0. That's because the bias weight is not really involved in what's going on there. And now what needs to be true? So we want the slack variables really are not supposed to matter at all, right? So you're going to need a great big 0 here. So what's going on here? This is n rows to deal with those slack variables. And then this is supposed to be a square matrix. So you've got n more columns over here. And what is going to go into all of these places? Now we have to think about what's going to happen on the right here with this one too. When I do G times Z, for that reason, this is going to have to be a big 0 too. So that when you do this multiplication, all of these slack variables get canceled out. And okay, I believe that's it. And this must be a 0 as well. Yes. Okay, so that's G, and now you could put this, now we're a large part of the way towards translating this into computer code. So we know what G is supposed to look like. G is you could initialize G to be like just a matrix of zeros that's D plus 1 plus n times D plus 1 times n, and then set these to be 1. And then we have to put in the little numerical dust as well to stop it from not being positive definite. Okay, and now let's think about how this part relates to that part. Okay, so there's going to be a mapping here. So now we're going to choose A so that A dot product Z comes out to be this quantity. Oh my God, there's a woodpecker pecking on my house. Whenever I start making these videos, weird distractions happen. Okay, so what is A going to be? You should pause the video and think about it yourself. A transpose. So what does A transpose care about? A transpose doesn't care at all about these W's, right? So it's going to be 0, 0, 0, 0, 0. It's going to be D plus 1 zeros. So that when you do this dot product, all of these W's get canceled out. And now there's going to be n more entries here to deal with the slack variables. And what are those going to be? Those are all going to be the constant c. Dot, 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 c. Okay. All right, so we've done a lot of the quadratic programming already. So we've determined what g and a are going to be to do this translation. And all right, so now there's only a little bit left. And so what is left is we have to think about before what we called a times z is greater than or equal to v. I hope you remember this. All right, and keep in mind what z is. Let me copy this so I can take it with me. And let's go down here and work on, I don't know where it's pasting. Paste there, son. There it goes. Okay. And all right, so that's our z. And now let's think about what a is going to be. What does a need to say? A needs to express that yi, let's just do it one at a time. y1 times wtx1 is greater than or equal to 1 minus zeta 1, right? So now I kind of remember that there was kind of a trick here. So instead of using this constraint, it's slightly, well, I don't know what to do if you don't do this. So let's algebraically manipulate this a little bit, and let's translate this into y1 wt x1 plus zeta. Gosh, I want to write that z so bad, but it's supposed to be a zeta. 1 is greater than or equal to 1. Okay, so now what we've done is, this can just be d plus 1 plus n ones. So we've solved the problem of what v is going to be. V is just going to be a column of ones. And now a times z is kind of the big question. All right, so let's start trying to sketch out what a is going to be sort of in block matrix form like we did with g. So let's think about this d plus 1. Is that what I should do? Okay, so this is going to be getting, let's think about this. This thing is going to be getting multiplied by this z character. And let me just copy z down here so I can use my brain better. This will be w1, w2, dot, 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 wd. It's going to be, that d is going to be small compared to n. And then it goes zeta 1, zeta 2, all the way out to zeta n. All right, and so let's think about how this is going to work. So this first row, when we do this matrix multiplication, this is going to basically dot product with this, and we want the result to be that. So how do we make that happen? I might be thinking for a minute here. You might want to fast forward. Okay, I thought of something. So what kind of stuff should we be putting in here? So we're going to be putting in here y1, x1, 1. Oh shoot, that bias is supposed to be there, isn't it? So I'll change this to a 0. That's the bias. That's just going to be 1. And then the next thing is y2. No, sorry. Stupid. This whole row is going to have to do just with and why did I write this sideways? I wrote this the wrong way. Sorry, bad teaching. It would be better if this was oriented vertically, because then we could really imagine the matrix multiplication happening. So this will be W0, W1, W2, dot, 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 WD, and then the zetas start zeta 1, zeta 2, dot, 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 down to zeta n, okay? And all right. So let's see. So I've got this. Now I'll have y1, x1, 1, and this will go on all the way up to, this is supposed to be a dot, dot, dot there, y1, x, d, 1. And now it's the stuff with the zetas. So I want to get just zeta 1 for this first one, right? For this, so I'll put in a plus 1 here. That will be a 1. Okay, and that will be a 0. And then there will be a whole bunch of zeros until the end. Okay, so that'll be the first row. Now what is the second row going to be? It's going to be y2, x0, 2, y2, x1, 2, dot, 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 y2, xd2. And now what we care about is it's going to be the second slack, because this is dealing with the second instance of data. So there's going to be a 0 there and a 1 there, and then a whole bunch of zeros. Okay, and we just keep doing this. We do this for all of the data instances. So that's going to be n rows of that. And I think that's it. Because we don't have to have, we have we could have more or less constraints, but we only need n constraints. So there's going to be one of those for every single row of data, and that'll do it. So now what happens over here is that this thing is basically a gigantic, what is it making there? It's making a big n by n identity matrix. Do you see how there's a 1 here and zeros there, 0 there, 1 there? So that 1 is going to move over. And yeah, and so how big is this thing? This is d plus 1, and then this is n, and it's n rows, and that's it. Okay, so now the linear programming is complete. So we've translated the soft margin classification problem into a quadratic programming problem. And the only thing left to do is to turn that into code. And so the place that you put that after you figure it out is right here in this little blank where SVM fit is. And remember that, so this is the hyperparameter C. Remember, but quadprog also has a parameter called C, which is the transpose of what we call A. So sorry for that. But if you come back here and you sort of imitate what's going on in this region where we actually did, right? Right here. So it's going to be kind of similar to this. You might need to work with ChatGPT on this, or this might be impossibly hard for you. Just because of not knowing Python and linear algebra. And if it's impossibly hard for you, do the best that you can, hand in something rather than nothing, right? So the first thing to do is to try something, and then don't be like, I don't want to show this to the professor because it's not perfect. Show it to me and get partial credit. I will rain partial credit down on your head so lavishly that you will not even believe it. But in order to get partial credit, you have to hand in something. And so, yeah, we pretty much just did the problem except for translating all of that from the paper into NumPy. And then the rest of this worksheet talks about what happens when you relax C. Look there, C just got a lot smaller. Now in this picture, C is 1/10, but in this picture, C is 1. And actually the slope of this decision boundary will change as well. It didn't really visibly change, but it can change. Now this talks about all the theory that we just went through. And now here you have a data set that is going to be very sensitive to your choice of C. I think it's actually not linearly separable. Then you implement SVM fit, and for various choices of C, you get different decision boundaries. So this is the weirdness with C equals 0, like it does kind of strange things. And then as C becomes more and more important, then you care more and more about correct classification. So look, C is now 1/100th, and that's pretty good. I believe that might be the choice that I would make for generalization. But if you force it to keep caring more and more, the margins get skinnier and skinnier, because what it starts to care more and more about is the slack. And when you make C really big, it doesn't care about generalization at all. It just cares about minimizing the slack. And that's actually not a bad decision boundary either. And then the video goes, the notebook goes on to say some more things. But I think we've said everything we need to say about actually implementing the SVM fit. And so I'm going to stop the video here.